Monia Ghobadi. She's a researcher from Microsoft Redmond, and she leads the optical networking research at Redmond. Her past work spans, she has a lot of experience. Her past work spans data center congestion control, RDMA, SDN, network measurement. Today you're going to hear about optics and programmable optics. And she received a PhD from University of Toronto and worked at Google's data center team before joining Microsoft Research.
Okay, thank you for the introduction. And thank you everybody for coming. I'm so happy to be here. Today I'm going to tell you the story of a couple of projects that I've been doing at MSR. And before I begin, I want to ask you, does anybody know what these colored lines are?
Fiber.
Fiber, yes. These are optical fiber cables connecting cities together across the world. The entire backbone of a service provider Google Facebook is actually running on optical fiber cables. At Microsoft, we have hundreds of thousands of miles of optical fiber cables going across the world, connecting cities and transmitting bits per second of data. In data centers too, every cable beyond top of rack cables is an optical cable, something like this. These optical cables at Microsoft, we have over 2 million miles of fiber cables only within data centers. And that's just a lot of cable. That's enough to go to the moon and come back a couple of times. So optics is everywhere. The scale of optics is massive, and they cost billions of dollars globally within data centers or in wide area. And so our goal is to improve the efficiency of our networks, maybe in the wide area network or maybe within the data center. And efficiency, we define it as dollar per gigabits per second. Basically, how much money does it cost for us to have a gigabits per second of bandwidth in our networks, right? Efficiency has been important. It's always been important, and that's why we have had, smart resource allocations in our data centers. We have had traffic engineering in wide area network, and we always want to improve efficiency. And so what I want to tell you today is that how do we get to this next level of efficiency? And I'm going to argue that with programmable topologies, we're going to go to this next level of efficiency in our networks, okay? So with that background, I want to give you an intuition of what I mean by programmable topology. To me, a programmable topology means a network that we can program its links, and we can also program the capacity of these links. So basically where the links go and what capacity they can carry, what sort of bandwidth they can carry, okay? Now assume that we have this very, very simple network. So 4 nodes and 10 gigabits per second connectivity between these 4. Now think about a traffic matrix like this. A wants to send to B with 20 gigabits per second, and B wants to send to C with 10 gigabits per second. Okay. No matter whatever programmability in the IP and application layer that I do with traffic engineering, resource allocation, or whatnot, the total throughput of this network is going to be 20 gigabits per second. And that's why, because, well, the cut in this network is 20 gigabits per second. But what if there's a world where we can literally change the network topology? What if there was a way for me to borrow a link from A to D that is idle and connect it to B? And that way I can carry 30 gigabits per second, right? I'm sort of augmenting the cut of this network from here to there, right? In another scenario, what if I was able to not change the topology, but change the capacity of individual links? Let's say that here, the link from A to B can actually carry 20 gigabits per second of capacity. So we'll change the modulation of that link and then carry 30 gigabits per second of bandwidth, right? So what I'm going to show you today is that actually these are possible. These programmabilities are possible. And I'm going to cover 2 projects that we've done in this space. First, I'm going to talk about a data center, reconfigurable data center topology. This was a SICOM paper last year. And then I'm going to talk about changing link capacity by having bandwidth variable links in the wide area network. And this was published at Optical Fiber Conference last year. Okay, let's zoom into data centers for a second. So if you look at the topology of today's data centers, it's sort of like this. There's like racks of servers with hierarchy of electrical switches interconnected with optical fiber cables, right? And there's a static provisioning of bandwidth between these servers, right? So because the topology is static, if we want to change this topology, somebody has to literally go to the data center and. So because of this, the ideal traffic matrix for this network is going to be a uniform and static capacity between all rack pairs in a way that the demand is not exceeding congestion. In this case, everybody is sending 3 gigabits per second capacity of bandwidth to each other, and everything is good. A non-ideal demand matrix would be a demand matrix where it's skewed and part of the network. Here, A wants to send to B 6 gigabits per second, and A also wants to send to C 6 gigabits per second. Right? Part of the network is congested, the rest of the network is sort of idle. Right? And so this is sort of a non-ideal traffic matrix. It's even worse if this non-ideal traffic matrix was changing in a very non-predictable way. Okay. So what we did was that we studied the traffic matrix of over 200,000 servers across 4 production clusters at Microsoft. These clusters vary between 100 to 2,500 racks in size. And what I'm showing here is the heat map of the amount of traffic that these clusters of these racks are sending to each other. Row corresponds to a source rack, and then column is a destination rack. And the color here is encoding the amount of traffic that a source is sending to the destination. So a horizontal row, means a rack that is sending a lot of traffic to other racks. And a vertical line means a rack that is receiving a lot of traffic from a lot of other racks. So the observation that we make is that you see much of this heat map is white, which means that many of these rack pairs are exchanging little to no traffic to each other. And then there's only some rack pairs that are basically active. So what does this mean? This means that a static topology with uniform capacity is basically over-provisioned for most rack pairs because they're not sending anything to each other, the ones that are white. And then it's under-provisioned for the hot rack pairs that are sending a lot of traffic to each other. And so this observation has been made in the past, and it was the motivation for having programmable topologies, when we want to dynamically provide additional capacity between hot rack pairs. Okay, so one question that we asked was that what are the sort of desirable properties of a programmable topology? What do we want for this programmable topology to, what sort of properties do we want for it to have? In the past, researchers have augmented this static topology with a dynamic topology like optical switches or 60 gigahertz bandwidth or even wireless links. And what you can see is that they're adding capacity, but there's this sort of a static division between the optical part of the network or programmable part of the network and the static part of the network, right? When we looked back at these traffic matrices, what we realized was that traffic matrices differ widely. So it's actually pretty hard for us to say in advance what portion of the network should be programmable and what portion of it should be static. Basically, we can't really tell, and then this portion these traffic matrices change over time. So this static division between programmable and static is kind of hard for us. And so what we want is that we want to have a seamless topology based on a single technology. What we want is that this static part and the programmable part, we want few limitations of the division between static and programmable parts. So another observation that we made was that source racks are sending a lot of traffic to lots of other racks. What we call this is elephant out theory. What this means is that we basically count the number of dark spots in one of these lines. So there's a source rack. It's sending elephant traffic to a lot of the destination racks. Count how many of these destination racks are there. Elephant out degree. In the CDF, elephant out degree of this cluster for a 5-minute window. If you look at here, what we see is that in this example, this cluster, 1/4 of clusters are sending elephant traffic to more than 150 other servers. What this means is that we should be able to create direct links to a lot of other racks. This is the property that we call high fan out. And then this high fan out also sort of motivates something else. It means that if I'm sending traffic to lots of other racks, I should be able to change between them very quickly too, which is something that we call low switching time. There was a question.
Yeah, so the question I have is, for these 4 programmable clusters you observed, are they similar in terms of the applications that they're running? Or are they,
They were actually different. They were running MapReduce jobs or index builders and storage with them.
Okay. And so my question is more about, do you observe any trends across applications, or is it going to be like this for all?
To be honest, the target is that we want to have any service anywhere. So we really don't want to build specific clusters for just one application. We want to be able to build a cluster and then put any sort of application. So one of the properties that we want is that we don't want to make any assumptions about the kind of application that the cluster is from. Any more questions up to here? Yeah.
It looks like you can cover maybe 3/4 of these elephant racks, or with, let's say, 5, 6, 7 out degrees. So then maybe you don't need the high fan out. I mean, if you kind of are you willing to just take 3/4 of the traffic out of the equation, or do you want to cover more with your optical switch?
I think this is one observation, and we kind of want to be, the higher the fan out, the better. And what we see here is that there is this trend of one rack talking to a lot of racks. So we basically want to embrace a technology that has higher fan outs. Okay, any more questions? So we looked for these properties in prior work, and none of the prior works that were based on 60 gigahertz or wireless or optical switches had even 2 of these properties. And so what I'm going to propose is a new way of building data centers, programmable data centers. It's based on free space optics, and it has all of these 3 desirable properties: high fan out, low switching time, and a seamless technology. Okay, so the proposal is called Projector, and I'll tell you where the name comes from. But let's take a look back at the data center topology again. Like I said, there's a static capacity, and the switches are connected with optical fiber cables. An optical fiber cable has a transceiver on each end, something like this. It's like a transceiver, right? And the transceiver has a laser and a photodetector. The job of the transceiver is to translate the electrical signal to the optical signals, and then vice versa. And so it has a laser and a photodetector for that purpose. In our proposal, we get rid of all the cables above the top of rack, and then we put mirror assemblies and DMD, digital micromirror devices, on top, and we disaggregate the laser and photodetectors that are in the transceiver, and then we shoot towards the mirror assemblies and receive laser light. More details about how the whole infrastructure works. But basically, overall, it's a free space interconnect. It has a fan out of 18,000 fan outs, which is 60 times more than the current optical switches. And it has a 12 microsecond switching time that is 2,500 times faster than the current optical switches.
So, question, does this free space optics have distance limitations then? Obviously.
It has distance limitations, but it's not, we studied it can go within a kilometer as well. The attenuation is actually 0.2 dB per kilometer. It's very similar to fiber. So for a data center, it kind of makes sense. Maybe city to city, it wouldn't make sense. But within the data center, there's no dust, there's not much distortion.
Exactly. Free space.
It's free space within the data center. It's sort of like think of free space within a building.
Yeah.
Okay, so the reconfiguration in this topology works with 2 components. One is that we use a digital micromirror device to redirect light, and I'll explain what it is. And then we use mirror assembly to magnify the reach. A digital micromirror device is a device that's built with Texas Instruments. It's used actually in every projection technology. It's a pretty commodity device. You can just go to the Texas Instruments website and buy it for about $100. What it is that it's actually an array of micromirrors. Each micromirror is 10 micron in size. That's 10 micron is like 1/10 of a human hair. Okay, and each of these micromirrors have a memory cell, CMOS memory cell, and this memory cell actually directs the direction of the light. So if there's a 0 in the memory cell, the mirror is going to be in the off position or 0 position. And if there's a 1 in the memory cell, the mirror is going to be in plus 12 dB position. So basically, there is this memory cell that we can upload 0 and 1s to it. And then depending on the 0 and 1 position, the mirrors are going to have on and off plus 12 degrees or minus 12 degrees position. And then we use this property to redirect light. How do we do it? Something like this. Here I'm showing a 3x3 DMD, digital micromirror device. And I'm showing that assume that this is the bit pattern that I've uploaded on this memory cell. Okay. This means that all of these mirrors are in the 0 position except the mirror in the middle. Right? Now, if I shine light with a laser to this DMD device, because of the diffraction property, the intensity of light is going to be high in one position. Okay. And then if I just change this pattern to a flip of this pattern, and then which means that all of these mirrors are going to just flip their position, and then use the same laser light is going to be focused somewhere else. So if you think about it, if I have a larger array of micromirrors, by changing the 0, 1 patterns, I can actually redirect light into various different locations. Right? And then the question is, how many total locations can I actually redirect light to? It turns out that it's actually equal to the total number of micromirrors within this chip. And for the chip that we had a 768 by 768 chip with these micromirrors. The chip is just yay big, but the mirrors are really small. We can have 589,000 different locations with this chip. And then we did some calculations and we realized that there's some crosstalk between adjacent angles. So we can't really recognize all of these adjacent angles. We have to get rid of some of them. And based on our calculations, with 18,432, we can actually recognize light from them. This is where this high fan-out property of a projector is coming from. Okay.
So you said plus 12 and you said minus 12 too. So how do you represent minus 12? Because of the symbols.
This is plus 12 and this is minus 12.
Oh, I see. So
Just the degree of this is something that TI has standardized.
No.
Got it? Nice. Okay. Okay, so, but even though these DMDs are very interesting devices and they can have 18,000 different angles, this is not without its challenges. One of the challenges of using DMDs is that they have a narrow angular reach. So what it means is that if I put a DMD here on top of the rack, the light actually has only a plus or minus 3 degrees of reach, which means that I can only reach out a vicinity of about a meter around. And so this sort of is negating all the nice properties of high fan-out and low switching pattern. But we realized that if I use angular mirrors here on the ceiling, I can actually magnify the reach of DMD to go farther and farther away. Right? So what we did was that we actually, depending on the data center layout, and depending on where we want to reach out, we can pre-calculate all of these angular mirrors. And we can put a mirror assembly on top of the ceiling that each mirror is corresponding to one destination. We can think of this mirror assembly sort of like a disco ball that has different mirrors and each of them have different angles. So the entire top of rack looks like something like this. We put lasers on top of the rack, and then we put DMDs in front of these racks and in front of these lasers. And then DMDs have different patterns that we upload using an FPGA. And then light is coming and it hits the DMD. Depending on the pattern that we upload on this DMD, light is going to hit one of the mirrors on the mirror assembly. And then the mirror assembly is going to reflect light to the photodetectors that are scattered on top of the racks. And so one rack is communicating with other racks by just changing the pattern on the DMD. This is the only moving part. The mirror assemblies are not moving. And so if I change the pattern, I'm going to hit a different mirror, and then changing the pattern and then hit a different mirror, and then that way I can reach all the other servers. And sort of this is happening across all the other servers are also communicating with each other using their own DMDs.
So the switch time is the pattern change time?
The pattern change time, yes. The switch time is the pattern change time, and I'll show you an experiment that shows that it's only 12 microseconds. Okay, so now that I've told you about how the projector interconnect kind of looks like, there's a couple of questions that we need to answer. One of them is that is it even feasible, or what is the feasibility of having something like this in a data center? The second question is that, let's say that it's even feasible, how do we route packets? Because we don't have cables anymore, and we have to decide on how to route packets between these different destinations. And the third question is, what are the cost implications of a fabric like this? So to answer the first question, we built a small prototype of a projector interconnect. And we also have to answer some robustness to environmental changes like vibration. To answer the second question, we devised a scheduling algorithm and then we simulated its performance. And to answer the cost question, we estimated the cost based on the estimation of individual components like a laser, photodetector. First, I'm going to show you about the prototype that we built. This is a 3-tor projector prototype. We're emulating 3 tors, tor 1, 2, and 3, and they're sort of distinguished by blue lines between them. Each of these tors have a laser and photodetectors and DMDs. I'm just going to zoom into one of the tors here. So we're using a commodity transceiver as our source laser. So the commodity transceiver is sending out modulated light. This is the DMD, and this is the FPGA that we use to program the DMD using a computer. So the light is going to hit the surface of the DMD. Then the DMD, depending on the pattern, is going to diffract the light towards either of these 2 mirrors, like mirror 1 and 2. And each mirror is angled in such a way that it's going to reflect light towards one of the destinations. Like, think of these 2 mirrors as 2 facets of a larger disco ball, if this were a data center. Okay. So if I zoom back out, all of these tors have the similar structures. They have a laser that sends light to the DMD towards their own designated DMDs, and then they diffract light to the mirrors, and then the mirrors reflect light. And then this way everybody can talk to everyone. So one of the biggest questions is that, okay, we're using air, so if you're using air, is it equivalent of air? Is air capable of carrying the same amount of TCP throughput as a cable or not? So we actually ran TCP connection using just a fiber cable or using a free space stick. And what we observed was that this is a CDF of throughput for an entire 1 day. Every 10 seconds, we're just measuring the TCP throughput. And we can't really see the difference between them, which means that, air, free space, and cable, they actually have the same TCP throughput. There's no packet drops or no packet errors during this experiment.
Do you have a graph, what distance in that?
So in the paper, we have a distance. We
Okay.
do experiments for 100 meters just by emulating sending light to the end of the hallway and then coming back.
Okay.
So I told you about the TCP throughput. The second question is what's happening with respect to switching time. What I did next is that I programmed the DMD to send light to one of the destinations, let's say in case tor 2. And then I upload a different pattern on this DMD so that it's going to send the light to another destination. And then I connect these destinations to an oscilloscope so that we can actually look of how long does it take for the light to switch. And here's what we see. In the x-axis is time and the y-axis is the received power on the oscilloscope. What's happening is that the blue line, at first, tor 1 is sending to tor 2. And so the power is high at the blue line. When I launch the switch command, this tor is not receiving any light, but after 12 microseconds, they're actually switching. And so the second tor is now, tor 3 is now receiving light. And so this is actually the loss of light time, the time that it takes one DMD to switch its pattern from pattern 1 to pattern 2. Yes?
The optical links work, but you have to reestablish a connect some synchronized clock.
That's a very, very good. What we're showing here is just loss of light. We are not showing packets. And these transceivers are actually not optimized for reconfiguring light. And if you put a transceiver in a switch and then turn the port off and turn it back on, it takes like 2 seconds for it to reestablish everything. So what previous work, the UCSD folks have actually hacked into this transceiver. They run a different transceiver with their own custom driver, and they show that switching time is actually negligible. Within a few microseconds, we can do it. So what we did is that, light is kind of stable here after 10 microseconds, and just to be conservative and sort of absorb that, we are assuming 12 microseconds. What I'm hoping is that in the future, transceivers are going to be capable of, do the locking faster. Locking is possible. Locking in nanosecond is challenging. Locking in microsecond is actually possible. Any more questions? Okay, so I told you about the test bed, and now I want to tell you about how do we route packets in this internet. Like think about a topology with lasers and photodetectors on it. I'm separating, like I'm just showing 3-TOR topology, but I'm separating the send side from the receive side just for clarity. So each of these TORs has like 3 lasers and 3 photodetectors. And the dashed line are showing all the possible links that I can establish. Right? And so the question is that how do we route packets? How do we create a topology with these free space links? And ideally what we want is we want a fast changing topology that every packet that comes to these buffers, we create a link and then we get rid of the packets. Right? But like if you notice, even though 12 microseconds is a pretty fast switching time, it's not nearly fast enough for packet switching. In 10 gigabits per second, a packet takes 1.2 microseconds to be transmitted to wire. So if I take 12 microseconds to switch and then transmit, 1.2 microseconds for the packet, it's not optimal. So what we came up with is a 2 topology approach. We have a slow switching topology or dedicated topology. This topology doesn't change as fast. It's sort of like a baseline topology. It changes maybe once a day or once a week. It's the default topology for all flows. And then we have a fast changing or opportunistic links. These opportunistic links are the ones that are getting rid of the large buffers for getting rid of the elephant. So the slow switching topology, you can think of it as an expander topology. We build an expander. We set aside a bunch of lasers and photodetectors. We build the slow changing topology, expander, factory, whatnot. And then we reserve the other lasers and photodetectors for a fast switching topology. Okay, so let me just give you one example of how this works. Assume the same example. We have 3 TORs. This is the send side, this is the receive side. I've got 3 lasers and 3 photodetectors. Okay, and assume that somehow I've decided that the red ones are for my dedicated topology, and I've created this multi-hop dedicated topology. Okay, and the ones that are not turned on, these are reserved for links. Okay, topology, like I said, is the default for all flows that get on this. These tools have virtual output keys. Their color shows the destiny. TOR 1 has 1 packet to TOR 2 and 3 packets to TOR 3. Like I said, initially everybody is going to go on this dedicated topology. And this topology is using k-shortest path routing to route packets. So what happens? TOR 1, the packet arrives to destined to TOR 2. It goes to TOR 3 because there's no direct link. And then eventually it makes it to TOR 2 through this multi-hop topology, right? And everything is good. What if suddenly we get a bunch of back-to-back packets that are destined to TOR 2? It sounds suboptimal to go through this multi-hop topology. And what we do is that we create an opportunistic link, which is a direct link from TOR 1 to TOR 2, and sort of get rid of this elephant flow in one go. Okay? Okay, so then now this is interesting. Let's say that somehow we decide on the dedicated topology, expander, factory, and whatnot. That's sort of an easy problem to solve. A harder problem to solve is the scheduling of these opportunistic links. Right? Now I have these lasers that are reserved for the opportunistic links here. And the question is, how do we find the right matching between lasers and photodetectors? So really the problem becomes, given a set of lasers and photodetectors, a set of possible links, find the set of active opportunistic links that are mapping this source destination traffic matrix to. So let's say here TOR 1 has traffic to TOR 3, so I want to create an opportunistic link from 1 to 3, and then 2 has traffic to 1, so I want to create an opportunistic link. So in a way it's sort of like a matching problem. And well, this is kind of cool because at first it kind of looks like a matching problem, and you have input queues and output queues, and then you have packets in the queue, and the problem is to find the right matching between them. So it's like a standard switch scheduling problem. There's a lot of solutions out there. There's the Blossom matching algorithm, or there's matrix decomposition algorithms, and they find matching between input and output points. But there's like two distinctions between our problem and standard switch scheduling problems. The first distinction is that these are centralized schedulers. They have centralized schedulers that knows the status of all the queues and ports. However, we don't want to have a centralized scheduler. The second property of these standard switch scheduling is that they're single tier. There is a layer of input and layer of output. For us, what happens is that we want to have a decentralized algorithm that, because we don't want TORs to talk to each other, we don't want TORs to assume synchronized clocks between each other. We want to have a decentralized and asynchronous algorithm. And our problem is sort of two-tiered problem. What this means is that the traffic matrix is between source TORs and destination TORs, but the matching that I have to do is between lasers and folded vectors. So it's like a matching, but there's a layer in between this matching. So to solve this challenge, what we did was that we extended the Gale-Shapley algorithm that finds stable matches between sources and destinations. Gale and Shapley wrote a paper in 1962 on college admission and stability of marriages that finds the matching between two sets of groups with a set of preferences from point A to point B. And we show that our algorithm is actually constant against an hindsight optimal offline algorithm that knows all the apertures. Okay, so simulated the performance of this algorithm. We use the standard that's the state of the art of routing and building data centers. Firefly topology. This is also interconnect that has been proposed SICOM 2014, and we simulated a projector interconnect. The result that I'm going to show you is for a 128 TOR topology with 16 lasers and 16 folded detectors on top of each track. 28 TORs, but I'm putting 16 lasers and 16 folded detectors on top of each TOR. So I have to decide at what point what am I doing. We then use the data traffic matrix to build the dedicated topology for these 128 TORs. The traffic matrix that would generate the probability of each TOR communicating with each other within these 5 minutes. But then beyond 5 minutes, because we didn't have the exact arrivals and departures of TCP flows, we just used the Poisson arrival with sort of realistic flow sizes to create individual TCP. So what I'm going to show you here is just one of the simulation results. On the x-axis, I have average load, and on the y-axis, I'm plotting average flow completion time, sort of as a metric of efficiency. And it's kind of clear that by increasing the average load, there's more packets in the queues, so the flow completion time has to increase. And this sort of happens for Fat-Tree and Firefly as well. What's interesting about Projector is that the average flow completion time is actually rising very, very slowly, leading into a 95% improvement in flow completion time compared to Fat-Tree. And the intuition of why this is happening is actually interesting because, Fat-Tree doesn't have any reconfigurability. And if you remember from the beginning, the slide that I showed the traffic matrix is extremely skewed, which means that Fat-Tree at some point doesn't have enough bandwidth, doesn't have enough links. Whereas with Projector, I just borrow links from this quiet part of the data center, and I'm going to give it to this hot rack pairs. Firefly is a reconfigurable topology, so supposedly it should do well in this case. But there are two reasons that it's not doing it well. One is that it's based on mechanical motors of changing the dynamic topology, which has a 30 millisecond reconfiguration time. So it's got a slow reconfiguration time. It also has a low fan out, which makes it to have to use multi-hop topology to create these dynamic links. Whereas for Projector, it's reconfigurable. It has a slow switching time of 12 microseconds, and it's got a high fan out. And all in all, these come hand in hand to making this level of improvement possible. Yes.
So I'm intrigued by the fact that Firefly actually performed first in Fat-Tree. So is it because of the, which one of the factors is causing it? Is it because it's slow switching time or is it because of the low fan out? That's
a really good question. I've contacted the Firefly authors and I've asked them about this. they didn't have much insight about why this is happening, and we think it's a combination of the two. I can't really pinpoint which part
Just
is,
to, just to know, it's interesting to know which factor is more, dominant in this.
That's a very good point.
Maybe we
And
can
my
choose a-
intuition is the slow switching time. Because if you're very slow for like 30 milliseconds, you're not sending anything. Whereas using multi-hop, especially if the rest of the network is latency. We have similar observations with respect to tail flow completion times or different traffic matrices. They also fan out and impact of switching time in network. So the feasibility and the routing. And third question is, how much does a projector interconnect cost? In the interest of time, I'm not going to go into the details, but what we did was that we estimated the cost based on our best assumption of how much does the laser cost, how much does the photo detector or a DMU cost. And our projection is that we're going to have a 25 to 40% cost savings compared to a factory topology. So the intuition to this though is, think of it this way, because we're getting rid of all the switching elements above the top of rack, we're getting rid of a lot of switches and a lot of cables and a lot of transceivers. And that's sort of where the majority of cost savings comes from. Right? Okay. So I want to switch gears to wide area network. If there's any questions on the data center part?
Sorry. There is a lot of free space optics and changing of mirrors. I know the DMD is the one that changes. That's the only thing that will change. So, do you have the exact cost breakdown in your paper someplace?
Yes, we have an exact cost breakdown for low estimate and high estimate. So we have, a very low estimate, and we think of what if this estimate is not right.
Sure.
Yes. The DMV is not actually that expensive. It's about $100.
No, not the DMD, but the mirrors themselves. The moving mirrors. What is moving in the mirror in this case?
No, the disco ball is not moving.
Okay.
So the disco ball is static. The DMV is the only component
That's
that's
more.
dynamic.
Okay.
Yes. And that's why the whole interconnect becomes actually
Okay.
and fast.
Okay.
Yes.
So you talk about the cost saving in the network, but if you look at the actual cost of the data center, most of it are actually servers. So like 40% maybe it would reduce the cost of the network, but if you look at the total cost of the data center, that would be a very small factor of the data center.
Totally right. Yes. The dominant factor in data centers today is servers, and network is actually only about 10% of the total cost. But if you put numbers together, it amounts into millions of dollars anyways. So if we can save a few millions of dollars, it's still desirable to do that.
I think if you go back to, I think it was slide, I think it was 18 or 28. Yeah. Anyway, so when you doing the temporary link.
Oh, I see. That would be like, this is 18, it would be 25.
Anyway, my question is that, so how do you determine to set up the opportunity link? Because you're looking at how many packets, how do you know how many packets? So you do that, like, you're doing per flow switching in a way, right? So how do you know how many packets are in that flow?
So each TOR has a virtual output queue.
Yeah.
And the virtual output queue, we
So
just
you
look
do
at the
that
buffer
virtual output
size.
queue.
Yes.
So when that's, but how, what has to be in order to decide that it needs to?
Yes,
or-
so we have a certain, I think 100 packets was something that we
Okay,
said.
that's
Yes. Yes.
I see that the experiments are conducted on an optical bench. Does it mean that in actual deployment there is some sort of calibration that has to be performed?
Yeah, I love that question. That's a great idea. Yes. We did it on an optical bench because the alignment is sensitive to vibration. And for us, in order to make this actually happen in real life, we have to have a closed loop calibration. So that, if there's a vibration, if somebody opens up the rack, or they're doing a maintenance and they, mess up the alignment, there has to be a way for the receiver to say, hey, I lost light, use a different mirror or use a different pattern on the DMV to, fix this.
is there any intuition why this is just a 12 microsecond? Like why the switching time is much faster than an optical switch, like 60x improvement? Where is it coming from?
That's also a very insightful question. The main reason is that the mirrors here have only binary positions, whereas in optical switches they're 3D maps, so they can have sort of any position in any angle. The Texas Instruments sort of optimize these devices to have 0-1 pattern, and that way we can have fast switching. Yes.
How does this scale in the number of racks? So plus topology, you can increase stages to sort of deal with larger size of topology. How does that apply to in your case?
So you're asking what would be the largest size of a data center that we can? I did some back of the envelope calculations in terms of number of lasers and photodetectors that I want to put in terms of the distance from the ceiling, the size of these, disco ball mirrors that have to fit, and in terms of, what is the real estate on top of a rack? Realistically, how many lasers and DMB they have? There's some real estate there. My estimate is about with 1,000 racks is possible. So imagine a data center with 1,000 racks. With, the back of envelope calculation that I did with commodity hardware, we can fit, enough lasers and enough EMVs and enough disco balls for 1,000 packages. Yes.
So the question is like whether the Tor is the right level to do the reconfigurability, because another approach is you have these multi-tier networks. You can do the same thing at the aggregation layer. What's the trade-off? Why would you want to do it at the Tor level, not at the another layer, like upper layers?
I like that question too. The way I think about it is the traffic matrix changing with the dynamicity in the traffic matrix. The higher up I go, there's more aggregation,
Yes.
so there's less changes in the traffic.
So doesn't it make your life easier to change the topology less frequently?
It's possible, but then the amount of flexibility that I would have in terms of Tor pair communication would be limited as well. So I think of that question with respect to optical switches. Where should we put optical switches? Because they have limited fan out and they have a longer reconfiguration time. With this, if I can do it at lower levels, it's better to do it at lower levels because there's more dynamicity.
I think the sooner the better, that would be the answer.
Right.
It's more like a distributed thing.
So if you have changes, if you have a lot of changes within the rack level, and if you can't do it, you better do it in the rack level. But with optical switches, because they have a longer switching time and they have a lower port count, we may be able to go higher up in the stack.
Does it change the topology frequently? Let's say that you can change the topology instantly without everything. Does it make the routing much harder? Because you need to converge, right? So even if you have a topology that can instantly change information to converge, right? So I understand switch latency of 12 microsecond helps a lot, but you still have the limitation of the routing, right?
Right. It comes all the way down to performance. If it's cheaper to build this network, and if it's easier, if it's better to debug it, and if flow completion times are going to be improved with the dynamicity and routing convergence, then we should do this. I think the way I think of this is that with this study, because we have single hop connectivity with our opportunistic links, there's no requirement for routing to converge. But with your point of going higher up the stack, somebody should do an analysis and figure out what's going to happen to routing if I have dynamicity on the higher up.
But I would think that you get a more balanced network you do at the very edge, right? So the idea is to balance traffic across the data center.
You would want to do it closer to the edge, yes.
So rather than just getting with some choke points after the application, right?
Yes.
So there's clearly a trade-off, right? You wouldn't do that and that's why it doesn't do that per packet, right? It does that, it says 100 packets.
100 packets.
I mean, so if you have 99, you don't do it.
Yes.
If you have some kind of special load pattern where you have a pair of racks, maybe some replication traffic, where you just need to send kind of the full bisection of the network of these two racks and just send between the two racks. Does the optical topology tend to support these types of scenarios, or because you have this reconfigurable topology, can you aim all the lasers between two racks to one another, or do you have more constraints?
Yes, that's actually one of the reasons that in our simulations we're much better than factory, if only two racks are communicating with each other, I can just create like 16 parallel links between them. Whereas in factory, you always have to have this, diverse set.
Fixed links.
Yes. Make sense?
Maybe one question.
Yes.
The rate of these opportunistic links, are they all constant or you can actually even read with that?
That's a good question, and it's gonna kind of touch. It's a really good segue for the second part of the talk. Right now, they're actually constant
I see, okay.
because it's just a data center transceiver. It's like this kind of transceiver. They're like $100. They don't have this, dynamic modulation. But let me quickly jump for the next 10 minutes. I want to jump into the second part. It would be slide 35. Yes. Okay. So I told you about area configurable data center, and now I want to kind of switch gears and tell you a little bit about the wide area network. So this is how we are used to looking at a wide area network from.
Yeah.
Start earlier.
But your timing is impeccable, actually. I'm just starting the second part of the talk.
Normally it starts at, normally it doesn't start.
It said in the email.
Yeah, it's
starting.
special 11 o'clock thing. So I keep.
Yeah.
You highlighted that. Otherwise, we wouldn't be here.
Okay.
No, it's not, I'm looking on the NetSeminar and it's, the time's not listed.
Okay, let me continue.
The website.
So we have data centers across the world, and then we are interconnecting these data centers together. And this is a kind of a view that I'm very comfortable with. It's the IP layer view of links are connecting data centers, big cities together. What's happening is that beneath this IP layer, there's like thousands of miles of optical fiber cables and there's like different optical devices in here too. And so, in order for us to understand this optical layer, first large-scale study of optical by studying the quality of signal of all of these things. Okay. So how does an optic look like? But let me just first sort of simplify. An optical wide area network consists of links and nodes, and these links are called segments, optical segments, and the nodes are called optical cross connects. Optical cross connects sits at points of presence. So think of it as major data centers. And their job is to collect data from different data centers and then WDM the signal into optical links and then put it in an optical segment. The segment capacity can carry like tens of terabits per second of bandwidth with multiple wavelengths. And their length in our North America backbone is between 5 to 2,600 kilometers. It just depends on the distance of between different points of presence that we have. So I'm going to zoom in into one of these optical segments with two nodes on each side. Each segment actually consists of two different fiber cores, one in each different direction. Okay, so literally physically, they're like two separate fiber cores. And then these different wavelengths are going across each of these different fiber cores in different directions. We call these wavelengths channels. And then depending on the distance, there's these amplifier nodes that are amplifying the signal, every 80 or 100 kilometers as light is going on. These amplifiers just add noise, they can fail independent of each other and whatnot. The way it looks like from the IP's perspective on the router side is that routers are connecting to these optical cross connects using transponders. And then the transponders have the job of changing the signal from electrical domain to the optical. And so to think about it as sort of like an easy way of thinking about it is that typically there's a one-on-one correspondence between an IP layer link and one of these optical layer channels or wavelengths. It's not always the case, but if you want to think about an IP link, think of one of these wavelengths that is going through the fiber. Okay. So our data set consisted of all fiber paths in North America backbone. We have more than 300 optical devices in different cities, and we had more than 4,000 optical channels or different wavelengths in this data set. What we did was that we pulled the channel quality factor or Q factor from these optical devices every 15 minutes since February 2015, and we're still doing this data collection as well. So Q factor or channel quality factor is a standard measure of measuring the quality of an analog signal in terms of its signal to noise ratio, or SNR. So the higher the Q, the better the quality of the signal and the better the SNR. Okay. So the question that we wanted to ask was that is our WAN efficient in terms of dollar per gigabits per second or not? And the answer was no. But there's something that we can do about it. So just the intuition of what I mean by what can we do about it and where gains would be coming from. Think of it as signal to noise ratio of 1. Here I'm plotting the threshold of different modulations. Okay, so we have 100 gigabits K, 150 gigabits per second, 8 quant, 16 quant. Okay. These numbers are the threshold for the SNR to be using these modulations. So, and its SNR is 6, it means that this channel can be decoded using 100 gigabits per second modulation. Right? If the SNR of 0.5, it means that yes, it can be, but it can also be 50 gigabits per second modulation. For a channel that has 15 and whatnot, it could be decoded with 200, 150, and 100. Where is the SNR of channels in a wide area, and where is the thresholds? PDF of signal to noise ratio that have on the same graph. What you can see is that, well, all of them have an SNR higher than the threshold for 100 gigabits per second because they were already all 100 gigabits. But what's interesting is that the mean is higher than the threshold for 100G. And 99% of the channels SNR that is higher than the threshold for decoding them using 150 gigabits per second. Better 43% of them can be decoded using 200 gigabits per second. So it's sort of like money on the table. We are conservative because we're static and we allow for large, and so we are using 100 gigabits per second modulation for all of these channels, whereas 43% of them can be just bumped up to 200G modulation.
So you're saying it doesn't automatically switch? I mean, like if you look at Wi-Fi, for example, based on SNR,
exactly.
It automatically just switches. And
yes.
I guess the other question is like, how dynamic is this SNR? Does it depend on like weather conditions or other conditions in like the
couple of slides. Yes.
temperature?
Yes.
I don't know.
So yes, we are going totally static because we didn't have it's easier to have a static allocation and just be conservative and allow for large markets. But what we're saying is that we can just have 1% to be 100G, 43% to be 200, and 50% to be 150. And what this means is that we just get 70% more bandwidth for free without doing anything else. And in terms of cost, it's not like the cost of 150G is twice as large. We're gonna be able to have cost savings as well. So if I have a deployment with all of the links to be 100G and it costs X dollars, deployment of 1% to be 100G, 56% to be 150, and 43% to be 200, we get a 60% cost savings. Percent of the cost of the original deployment.
Is it conservative because they're trying to avoid failures? And presumably, sending a truck out could be ridiculous. So that could immediately eat all. If you have
this dynamicity. We don't have dynamic way of allocating our modulation based on the SNR that we measure. And so that's our proposal, that if you're static, you have to be conservative because you have to allow for large margins. Because of what you just said, there could be something that happens and we didn't anticipate it, and we can't send a truck in the middle of the US. So, but what we are proposing is that if we have a way of measuring SNR, just like what wireless folks do, and then adjust the modulation based on the SNR, then we can just get more bits using the same fiber path. And fiber is really, really expensive, so we don't want to buy new fiber, we just want to use this fiber to its full potential. Okay, I told you about these 50 gigabits per second jump, but the natural question is, well, what if I had 25 gigabits per second jumps? What would be the bandwidth gain there? The bandwidth gain ends up being 86%. And then the question is, can we go further and further? Today, the hardware exists to do 50 gigabits per second jumps. The industry is kind of moving towards 25 gigabits per second jumps. And what we show is that with 1 gigabits per second jump, there's a 99% bandwidth gain. But the industry is actually kind of far away from getting these 1 gigabits per second jumps to materialize. So
not just hardware. I mean, these are algorithms, new algorithms that you might need to create as well.
We need to have programmable algorithms and forward error corrections. Yes. But to your point, your earlier point of how fast these things change and would we need modulations for different wavelengths over time and whatnot. We studied of SNR over different fibers and over different wavelengths that are going through this. And our results show that we are different modulations per fiber, per different segment, and that are going through the same path. The devices are called bandwidth variables. These are kind of new areas that are coming to the market since 2015. They adjust capacity using variable coded modulations, and they have, like I said, rate adapted forward error correction. Okay. And so the impact of this study actually, moving forward, all of the transponders that we're going to buy are going to be bandwidth variable. We're going to totally shift from static transponders to dynamic transponders. Like I said, in this case, it's going to result in 70% capacity gain, 60% cost, and of course 25% power and also space reduction. So, in order to have 200 gigabits per second, I don't need to have two modules. Like I just have one module that is capable of doing 200 gigabits per second. And then there's this nice thing about this study was that we built this monitoring muscle in the WAN and in the data centers. And we didn't used to measure our optical layer in WAN or in data centers. And because of this study, when we created this, monitoring muscle, then when data pours in, then there's new results and new stuff coming in too. For example, in data centers, we showed that because we started monitoring the optical layer, we have an upcoming SIGCOMM paper that talks about mitigating packet corruption in data centers. We also have, from our data centers, we have a data center designed with variable bit error rate, sort of like something that you were touching on. What if I can actually change the bit error rate of data center links, and what does it mean for a data center link to have unreliable, links? Then in the wide area network, because of this measurement, we actually have results that we can predict optical layer failures that we presented last year at IFC. Okay, with all of this, I want to conclude. I've tried to convince you that networks, both data centers and wide area networks, need to be efficient, and programmable topologies result into more efficient networks. I told you about our reconfigurable data center that we program the topology, and then we get performance gains there, and having bandwidth variable links to get performance too. I want to say 2 sentences about sort of the world that we're headed. In terms of, in the wide area network, there's a lot to be done. Changing the modulation is just one thing, but there's this world of, optical layer and IP layer. And by cross-optimizing these layers, we can even change the topology in the wide area, not using free space links, but using these programmable devices that are, that are pretty new, but you can borrow wavelengths from one optical link to another optical link. And that sort of realizes the full potential of having what we call an optical software-defined network in the WAN. But with that, I'm going to end it, and I'm happy to take any more questions. Anything else?
I have one more question
Sure.
in the first part of your talk
Sure.
in your simulations. So you've shown that the average flow completion time has decreased as a function of load on the network.
Correct.
Usually, it's like the standard question. When you look at average, it tends to weigh the large numbers. If you reduce the flow completion time of the large flows, it would affect your average.
Yes.
Have you looked at how you affect the small flows, or?
That's a really good question. We don't affect small flows as much. If you remember the two topology approach, when I had the dedicated topology is this multi-hop topology, but think of it as expanders, right? And so small flows are going to go through the same sort of dedicated topology, multi-hop and whatnot. And the large flows are the ones that are benefiting a lot from these direct links. So yeah, we looked at it and we're not hurting the small flows at all. Yes.
Given the importance of these systems, like what are the main challenges in the adoption of these systems?
So in the data center one, I think one of the things that you touched on, sensitivity into, practical challenges, basically. Now, it's all the matter of practice now. We have to be able to show that there is a way of calibrating when a link is loose. That's one of the biggest challenges that we have to be able to prove that there's a way of fixing.
Shema, this is the beginning you were talking. Did you say free space? Like you're using like laser or microwave links? Like
laser
yeah.
So we basically get rid of everything here,
and
then we put lasers.
That's cool. Regarding the optical SDN and the WAN, this isn't necessarily a question, but it's I agree completely. Like I mean, it's what what people in lab are trying to do with some of the disaggregated road stuff is basically do, I mean, they're all boxes at the end of the day, so this two-layer topology thing, like, I think the main reason it exists is for sort of simplicity and because of sort of historical reasons where everything was configured statically, but once you have programmable devices, it's obvious that you want an end-to-end optimization.
Yeah, absolutely, I totally agree with that. Yes. Anything else?
Thank you very much.
Thank you.
Thank you.